Okay, I'm going to walk through examples 3 through 6 from notes 1.2. So example 3 we skipped in class. So we're going to convert the vector 5 at negative 80 degrees to component form. So to begin, I'm going to sketch the vector. And remember, when you draw the angle, it's always from the positive x-axis. Negative 80 degrees means that we're going to be rotating clockwise or downwards from the positive x-axis. So I'm going to draw my angle at negative 80 degrees. And then I'm going to draw a vector. I'm going to label it. This is, its length is 5. This vector isn't given a name, so I won't give it a name in my diagram. And then I'm going to draw in the right triangle by dropping really an altitude to the positive x-axis. And then I'm going to label my components x and y, x being the horizontal distance, y being the vertical distance. And we know the hypotenuse is 5. So I'm going to label my sides. That'll help me with my right triangle trick. So hypotenuse, x is my adjacent, and y is my opposite. It's going opposite the triangle from the 80 degrees. And to put this in component form, we really need to find x and y. So I'm going to use right triangle trig. So I can say that cosine, let's do cosine of 80 degrees is going to be adjacent, which is x, over hypotenuse, which is 5. And I can multiply both sides of the equation by 5, so I get x equals 5 cosine 80. If I punch that into my calculator, making sure that I'm in degree mode, I get x is equal to 0.87 units. Let's do the same thing for y. So I'll have sine of 80 degrees is equal to y, the opposite side, the length of the opposite side, over 5, which is the length of the hypotenuse. And then I'm going to do y equals 5 sine 80 degrees, simply multiplying both sides of the equation by 5. And if I enter that in my calculator, I get 4.92. And now we need to think about the signs, whether they're positive or negative for each of the components. So my vector, if I look at the x component should be a positive value, right? Because I'm going in the positive x direction for this vector. So 0.87 is correct. But for the y component, this 4.92, this has to be a negative value because I'm going in the negative y direction. So I have to change the sign of my y component to be negative 4.92. So I'll write that down. You have to change sign of y component because, now let me make that a little clearer, because vector is in quadrant 4, where we have a positive x and negative y. I'm going to go ahead and redo example 4 because in class the screen sharing was very delayed. So I'll walk through this example one more time. So we're asked to convert a vector from polar form to, from component form to polar form. This vector q, I'll put a little harpoon on top, is in component form 3, 7. So it's 3 horizontally and 7 vertically. And it's going to start in standard position. I'm going to sketch it. It starts at the origin, and it's going to go up to the point 3, 7. I'm going to drop in altitude, going back to the horizontal. The right angle is always going back to the horizontal, not to the vertical. So the horizontal component is positive 3. The vertical component is positive 7. And this is my vector q. I will label it. We don't know the magnitude. We don't know the direction angle. So I'm going to label this angle theta, going from the positive x-axis. And sometimes you'll see the magnitude written as r. We can write it as c. I'll write it as c because that's like Pythagorean theorem. So the magnitude of q this is what we want to find. So in order to find this, we'll use Pythagorean theorem, just like we did in class. So I'll call it C. So C squared is equal to 3 squared plus 7 squared. And 3 squared is 9, 7 squared is 49. So 9 plus 49 is 58. If we take the square root of both sides, we'll get C equals rad 58. 58 is 2 times 29, 29's prime. So I can't simplify this. If you like a decimal approximation, that's about 7.6. If you'd be happy with that value, that's okay. And now we want to find the angle. I would not use this rounded value for the magnitude of C. So actually, I'm going to call this the magnitude of Q. Instead, I would use 3 and 7. So to find theta, 7 is the opposite side, and 3 is the adjacent side. So in terms of right triangle trig with SOHCAHTOA, we know the opposite and adjacent. So let's use tangent as our ratio. So we're going to have tangent theta is the length of the opposite side, which is 7, over the length of the adjacent side, which is 3. And now to undo tangent, we use inverse tangent. So we'll have theta equals tangent inverse of 7/3. And remember, when we want to get an angle out, we're going to be using an inverse trig ratio. If we punch this into our calculator, making sure we're in degree mode, we will get 66.8 degrees. So vector Q is going to be 7.6 at 66.8 degrees, or if you want an exact answer for the magnitude, it would be rad 58 at 66.8 degrees. Okay, let's go on to examples 5 and 6, where the vector is not drawn in the first quadrant. So next page. So example 5. So once again, we're given a vector in component form. So we're given the vector W, which is -2, -5. I'm going to go ahead and sketch that vector. So -2 in the x and -5 in the y. So we'll draw in our vector. I didn't draw it so well. I'll redraw my vector. Okay, that looks a little better. I will draw in an altitude, which is always going back to the x-axis. In this case, it's going to the negative side of the x-axis. Theta is always inside of our triangle going to the x-axis, not the y-axis. I'm going to call this theta prime because it's really not our angle, it's our reference angle. So theta prime is the reference angle, and we're going to have to adjust that because our vector is not in the first quadrant. I'm going to label the side lengths of my triangle. So -2 is the horizontal and -5 is the vertical. And in terms of my reference angle, the -2 is my adjacent side length and the -5 is the opposite. The hypotenuse is what we need to find. So that's going to be, we could call it C for now. And we need to find theta, which first we're going to find theta prime. Theta is actually going to be this angle going all the way from the positive x-axis. It's going to be theta, which we'll find later. But I'm getting a little ahead of myself. So let's begin. Let's first find the magnitude. Okay, so I want to find the magnitude of W, and we're going to use the Pythagorean theorem, just like in the last problem. So I'm going to say C squared is equal to -2 squared plus -5 squared. So A squared plus B squared is C squared. Remember, either leg doesn't matter which one is A and which is B. So we'll get 4 plus 25, which is 29. Taking the square root of both sides, C is equal to the square root of 29. If you like a decimal approximation, that's about 5.4. Either way is fine with me. So this is the magnitude of W, is rad 29, which is about 5.4. Okay, now we need to find the angle. So looking at our right triangle, we're going to use the -5 and -2 because those are exact values, not the magnitude that we just found. And so in terms of SOHCAHTOA, we want to use the -5 and -2, which are opposite and adjacent. So I can say that tangent of theta prime, the reference angle, the angle inside my triangle, is going to be the length of the opposite side, -5, over the length of the adjacent side, which is -2, which is 5/2. So theta prime is going to be tangent inverse of 5/2. And if we enter that into the calculator, we find that this angle is 68.2 degrees. That's the angle inside the triangle, right? But the angle that we really want, right, is this theta here, which goes from the horizontal all the way to our vector. So theta is actually going to be 180 degrees plus 68.2 degrees, which is 248.2 degrees, right? Our angle is in quadrant 3, okay? So this is our actual angle for our vector, which we need to adjust, right? So here you have to think about the angle and make sure the output from the calculator makes sense, right? So have to think about the angle and adjust it based on the quadrant for the vector. So when we're in the first quadrant, what the calculator gives us is fine. When we're in a different quadrant, we will need to make an adjustment. So I'm going to summarize. Vector W is rad 29 at 248.2 degrees, or if you want the decimal approximation, you could also say it's 5.4 units at 248.2 degrees. Okay, so if it's an exact answer, just write rad 29. That's perfect. Okay, example 6, we're going to convert another vector from component to polar form. And when it's not in the first quadrant, we have to do a little extra work. Okay, so I'm going to go ahead and sketch this vector. It's 2, -7, so it's 2 in the horizontal direction and -7 units in the vertical direction. So I'm going to draw in my vector. I'm going to draw in an altitude to make a little right triangle. So the right angle is always relative to the horizontal. The angle here, I'm going to call it theta prime. That's my angle inside. I hope you know that little apostrophe notation. That's called prime. Theta prime is inside the triangle. My side lengths are +2 in the x direction, -7 in the y direction. So let's find the hypotenuse first. So I can say c squared is equal to 2 squared plus -7 squared, which is 4 plus 49, which is 53. 53 is prime, so I can't simplify the radical. So c is equal to the square root of 53. If you would like a decimal approximation, that is about 7.3 units. So we found the magnitude. And now we need to find the direction. So working with theta prime, the angle inside the triangle, and in terms of SOHCAHTOA, the 2, I'll fill this in, 2 is my adjacent. I get a pen. 2 is the adjacent side, and -7 is the opposite side. I want to use those because those are exact values. So tangent theta prime is -7 over 2. So theta prime is tangent inverse of -7/2. And that turns out to be -74.05. And then I have to think about this angle. Is this the correct angle? Did my calculator give me an output that makes sense for quadrant 4? And looking at this does make sense because theta prime is this negative angle, -74.05. So this makes sense, so I don't need to adjust it in quadrant 4. So our vector is going to be, what do we get? 7.3 units at an angle of -74.05 degrees. Or if you want to use an exact value, rad 53 at negative 74.05 degrees. So in quadrant 4, our calculator actually gave us the value that we wanted. When we were in quadrant 3, so if we go back right to the last example, our calculator did not give us the right angle. It gave us 68.2, which would have put us in quadrant 1. Also, if we're in quadrant 2, which I think there'll be some examples later, you'll also need to make an adjustment. So the important thing is you're going to use tangent or inverse tangent to find the angle, but then look at the value that you get from your calculator and make sure that that angle actually falls in the proper quadrant, and if it doesn't, then adjust it.